Hello, this is Peter Yerkut. I want to talk to you briefly about term document matrices, which are one of the principal tools of text mining and forms the basis for the various mining procedures. For instance, clustering, um, dividing documents into categories so that within a category the documents are like each other, and when they're not in the same category they're different. Predicting or classifying a new document. If you've got a couple of clusters or groups of documents, to which one of those is a new document likely to belong? And it forms and term document matrices form the basis for information retrieval in the way that Google works. Namely, you have a bunch of documents that you're familiar with or have in your document database, and a new document comes along, which could be as short as 1, 2, or 3 words in a search string, and you take that new document, even though it's very short, compare it to all the documents you have, and you retrieve the one that's most similar and likely to have the same words and content as the little short search string that you put into the search box. Basically, a term document matrix has a bunch of documents, and here we have an example of like 9 of them that I got from a paper by Landauer and his folks. He's one of the leaders in text mining and semantic analysis. And so you have a bunch of documents, and then you take words from these documents and make a column for each word, and the content of the term document matrix contains the number of times a word appears in a document. So for instance, system appears once in document C2, C3, and twice in C4. And this is sort of a way of maybe making a mathematical representation of the content of documents, even though there's no semantic analysis involved in building this matrix. It just takes words, compares them, and if they're in the document, you make a mark, and if they're not, you don't. Now, I didn't pick all the words in this document for this particular matrix, and the idea is that you only want words that appear in a moderate amount of documents. If you have a word that appears in all your documents, it has no power to distinguish between them. Just because there's 25 copies of the in one document and 35 in another, they're still not going to be able to really help you which one would match something else. On the other hand, if you only have one, if a word appears in only 1 or 2 documents, chances are it's a rare word, maybe a specialized word, and it's unlikely to come up in new documents, unless they're within a topic, in which case, you think that topic becomes a group of documents. So you want words that appear often enough in enough documents that you can tell the documents apart from each other, but not so many that it becomes meaningless in terms of distinguishing. So the notation is as follows. The index I, as usual, will be a row index, row 1, 2, 3, 4. The index J will be the column index, so it'll go from 1 to 12. And TF, IJ, which stands for term frequency in document I of word J. So TF 27 would be row 2, column 7, and the frequency of the 7 term in document 2 is 0. And that basically is the term document matrix. what we've done is we've created a numerical representation of a document by the frequency of its words, and this now is a tuple. You can think of this as a table in a relational database management system, and we can treat these as vectors, numerical vectors, and we know how to calculate distances between vectors. There's a couple ways of doing it. Jacquard distance, which you might want to look up, or cosine distance. In effect, we take an inner product of this thing and divide it, normalize it in a certain way, take the inverse cosine, and we end up with an angle that tells us how far apart these two vectors are. So we now have a way of grouping documents by their relative distance from each other. It's not a physically easily comprehensible distance, but since we've got 12 dimensions here, our visual intuition really fails. But if you reduce this thing to maybe 3 documents or 3 terms, we can now think of these first 3 documents. This one is at the origin. This one is where x equals 1 and y equals 1 and z equals 0, and this one's in the same place. And this one is a little bit further away along the x direction, and at the origin in the x and y, in the y and z direction. So our 3-dimensional visualization can apply, and we get some idea. Now, of course, in the 12-dimensional space, we really can't picture it. In any case, this is the basis of the term document matrix. Now, the frequency of a word by itself may not actually do a lot to distinguish these documents, because, like I said, if it appears in a lot of documents, it's more valuable than when it only appears in one, but less valuable than if it appears in all documents. So there's a variety of weighing schemes of how to reevaluate these numbers so that they not only show how they fit in with a particular document, but how spread out they are over the whole document corpus. There's a couple ways of doing this. Bayesian probability is one way, using information theory and you know, the law of the entropy equations is another way. But one of the original ones was something called inverse document frequency. And that becomes about, we begin with document frequency of a term J, and that's just how many documents that J appears in. And then so here's a row of document frequencies. Term 1, system, appears in 3 documents. Term 2, user, appears in 3. And then we've got a couple, there's 2 here. Now I have chosen only documents that appear in at least, terms that appear in at least 2 documents. I restricted them because a term that only appears in 1 document is, as I said, not as useful as the others. So here we have document frequencies 3 to 2. And the weighing factor is actually a logarithmic. So let's look at the equation for term document, inverse document frequency. If you look at the formula, it's a log function, and A26 turns out to be the number of documents I have. So we take the number of documents, we divide it by how many documents this term is in. And the reason we do it that way instead of the other way around is because we get positive logarithms if we do that. The logarithm, if the word is in all 9 documents, the ratio is 1 and the log is 0. So that's you know, a weighing factor. If it's in only 1 document, then it's 1/9, and I mean 9, and the log of that is what, about 2, 3? Well, no, it's somewhere between 1 and 2. So chances are the log are all between 1 and 2, and here they are. So the inverse document frequency is the number of documents, 9, divided by how often this word is in the document, 3. That gives us a value of 3. And then we take the log of that, and we get 1.10. Now, so that's a weighing factor. So here, this document, this is a pretty important word. So the 1/5s turn out to be weighing factors that are of some sense important. And now what we do is we multiply each of these by the term, by the term frequency. So we take these weights, multiply them by these weights, and we get a weighted term document. And this is now called a term document inverse document frequency matrix. And this one contains frequencies weighted by their, quote, importance, as shown by the document, by the inverse document frequency. The reason we use a log, because it's based on word frequencies, and they have a distribution. It's called Zipf's law. And let me see. And here, so here's a Wikipedia article about them. If you notice that they're basically shown on a, God, I hate this, on a log-log scale. And that's what brought up the notion of using an inverse document frequency based on logarithms of the ratio or the proportions of the inverse proportion of the frequency of a word in a document. And now, again, we treat these as vectors, but now they're weighed. And so chances are we will get a little better representation. Incidentally, these are now vectors, but you can also think of them as a statistical database with these things as variables and these things as entities, and we can now do correlations between entities, and we get this matrix up here. And what's interesting is that there are correlations of a moderate size, 0.5 is actually put up, between a document in group C, which are these first 5, and document in group M. So here's a correlation between C2 and M3, and if you want to look through it, you might actually discover some ideas about why this is so. The semantic analysis that is the subject of this paper uses a mathematical treatment of where the columns are basis vectors and the rows are basis vectors in their space, and we have something, and we get a matrix that indicates a rotation of the space of data so that we get high variances in some directions, and they will find these kind of correlations between C2 and M3, and that's the subject of the paper. But basically what I wanted to concentrate on is the term document matrix and how it's weighted. And then below here I've used all the words, and you can do some comparison between having chosen just words that are greater than, that appear in more than 2 documents, and words that don't. So this is a fairly simple construction. It takes a lot of counting. It appears in most text mining software like SAS, for instance, and you'll see in the SAS results these kind of term document frequencies. So that's about it. Take a look through this, and if you want, go find the paper, look at Zipf's law. And like I said, this is the basis for a lot of text mining. Thank you.